Hi, everyone, and welcome to Astro at Home, presented by Discover the Universe. My name is Lindsay Mann, and I'm really excited to present our speaker to you today. But before we get to that, I want to give you guys those ground rules that we have, which are to respect one another in the chat and not to spam the chat. If you break those rules, we'll either delete your message or we'll put you in a 5-minute timeout. We also really want to get your questions. Our presenter today is going to take questions throughout the presentation, so you can send them to us, and we'll get them to him right away so that he can answer what he can. Today we are joined by Jesse Rogerson, who is with the Canada Aviation and Space Museum in Ottawa, and he's going to be talking to us about some of the stuff that's been in the news about astronomy lately. Jesse, I'll invite you to turn your camera on. Sometimes it's, there we go.
Okay, can everybody see me?
Yeah, we're good now.
Okay, great. Okay, cool. Well, thanks for the introduction. I am Jesse Rogerson. I work at the Canada Aviation and Space Museum in Ottawa. So I live in Ottawa, Canada. I don't know where everyone else is around the world, but I'm excited to chat with you. YouTube is so useful for something like this because anybody anywhere can watch. And I have two things to talk about, and I definitely like questions at any point. So throw them in the little YouTube chat room there, and myself and Lindsay will make sure that I see them. And I grabbed two things to talk about today because they're two kind of similar stories in their science, but they are very different in their subject. So let's dive right in, and we'll start with a video. So this is a video, and you can see it's the night sky, and we're zooming in. So we're zooming into you can see the Milky Way is really dense along the top there, but we're zooming in just below the plane of the Milky Way into a section of the sky. Now, it's what blows my mind. I'm an astronomer, and it still blows my mind that as you zoom into these patches of sky that seem so dark, there's still thousands of stars. So we look at these thousands of stars just in this little section. And we're zooming and zooming in, and we can keep seeing more and more and more, and it seemingly goes on and on forever. And all of these stars that you're looking at are part of the Milky Way galaxy, the galaxy that we live in. And this one star right here in the center is the star that I wanted to talk about. It's called HR 6819, and it's actually two stars, or at least originally thought to be two stars. It's a double system, or a binary system, and many stars in our galaxy live in binary systems, which means it's two stars that orbit each other as opposed to one star just off on its own. So, like our sun is a single star all on its own, and there's a bunch of planets that go around it. We're one of the planets, and it's just the one star. In many stars in our galaxy, it's two stars that orbit each other, and they may or may not have planets with them. It depends on the system. Some binary systems do have planets that we've discovered, but the point is that a binary system has two. They go around each other, and it's about 1,000 light years away, this specific star system, HR 6819, about 1,000 light years away. And what that means is that it takes light 1,000 years to travel the distance between that star and us. So the light you see in this picture, that blue dot right in the middle, that blue light took 1,000 years to get to you, traveling at light speed. It's very, very far away. And the cool thing about this binary system, these two stars that are orbiting each other, is that it has a magnitude of 5.33. In astronomy terms, an astronomer uses the unit of magnitude to measure the brightness of something to our eye on the sky. And so a magnitude of 5.33 is actually visible to our naked eye, which means you don't need a telescope to see it. You could see this binary system completely without any help. No telescopes, no binoculars, nothing. It's just faint enough, just bright enough to be visible to our eye. But it is in the southern sky, which means you'd have to be south of the equator or very close to the equator to be able to see it. I have actually a picture here. This is where it's located. So if you look right along the top here, there's the constellation of Sagittarius right there. There's the constellation of Scorpius, and south of those constellations towards the southern sky is the Telescopium constellation. It's a constellation you don't get to see if you're in the north, but if you're in the south, you're quite used to it. And right in the corner of Telescopium, right there, is a circle showing you the location of the binary system that I'm talking about. Now, here's what's really cool about a binary system. So here I have a video. Okay, it's going kind of fast actually, but you can see they have two stars here, and when they orbit each other, normally when you have a planet orbiting a star, like when we orbit the sun doesn't really move all that much. We go around the sun, and it takes 365 days, 1 year, for us to go around the sun, and that's one orbit. That's because we're really small. We're really small compared to the mass of the sun. We don't actually affect much, do much gravitational work on the sun. But the planet Jupiter, which is pretty massive and kind of comparable and a little bit closer in mass to the sun, actually tugs on the sun just a little bit. Our star, the sun, actually does wobble just a tiny amount as Jupiter goes around it because of the gravitational interaction between the two of them. But it's not that big of an effect. And for most talking about the solar system and how far away things are, we kind of picture the sun as stationary in the center of our solar system. But when you have a binary system, like two stars, their masses are so comparable in size that it's not that one is orbiting the other, it's that they're both orbiting their common center of mass. So in this video, you can see in this animation, you can see the big blue star in the center the red star is going around the blue star, but the blue star is going around a point out in space, which is the common center of gravity between the two stars. So they're both going around each other. They're both going around that green dot right in the middle. And that is a very different idea than our Earth, orbiting the sun, and with the sun not really moving all that much. But that's because these two are more comparable in size, these two stars. Now, one other thing I want to point out here is that you notice that the blue star takes exactly the same amount of time to go around its orbit of the green thing, the green dot, as does the red star. They both take the exact same amount of time to go through this orbit. They have the exact same period. Okay? And that's a really important thing to know, because when you look at a binary system like this and you see that the blue star does a wobble in, say, X amount of months, and the red star does a wobble in the same amount of months, you know that those are the only two things that are there. It's just those two things orbiting each other. They have the same period. Why is the sky dark at night? Okay, there's questions. Okay, I'm gonna pause this. Okay, Lindsay sent, oh no, I need to go back. Okay, there we go. So the question is, why is the sky dark at night when we have so many stars? Someone told me it's because of dark matter, but I still don't understand. Good question. So that question is, when you look up at the night sky and it's dark, well, your eyes are only capable of seeing a certain brightness. There are billions of stars in the Milky Way, and they're all shining nice and bright if you're really close to them. But the further away we get from them, the dimmer and dimmer and dimmer they get. And if we are far enough away from them, then they will be beyond the ability of our eye to see. And so when you look up into the night sky, the direction you're looking, there's billions of stars in that direction, but most of them are too faint for your eyes to see. If you brought out a telescope and you looked in the same direction, you would see many more stars. And if you got a bigger telescope, you'd see many, many more stars. And if you got out the biggest telescopes in the world, you'd see even more stars still. So dark matter doesn't have anything to do with it. It's the fact that our eyes just are incapable of seeing the dimmer ones. However, there are things that actually do block starlight, and that is dust. So if you go out into the night, into a field in the middle of the night, and you happen to be in a dark enough sky to see the Milky Way with your eyes, then you would see, in fact, actually, we can go back to my video. So if you look on this video, there's the Milky Way there, but you can see there's dark stuff that's weaving its way through the plane of the Milky Way, and that is dust. Big, huge, massive clouds of dust that is so thick that the light from the stars beyond them can't go through. It gets blocked by the dust, and we're seeing the shadows of the clouds of dust in the Milky Way. But pretty much everywhere you look up in your sky or on this image of the Milky Way here, there's stars in those directions. It's just that our eyes aren't good enough at seeing the faint things. What are the numbers under the blue circle? Oh, good question. I don't know what those numbers are. I have no idea what those are. Probably something related to orbital parameters. So like how long it takes to go around. I stole this video from Ohio State University, and it's just to talk about how two stars orbit each other. And I wanted you to understand, really important to understand, that when two stars orbit each other, both stars have the exact same period. Okay, if there's nothing else there, they both have the same period. It takes just as long for the blue star to go around as it does for the red star to go around, even though they're at different distances. Okay, so the story I want to tell you about here is about the star system HR 6819 and a group of astronomers that were looking at the system because they wanted to study binary systems. So what they did is they pointed their telescopes at the system and they measured the orbits of the two stars that were there. That's this star right here and this star right here. And what they realized when they did this is that the star that's closer to the center of the system has a different orbit than the star at the edge of the system. It's different lengths of time. This star here was orbiting with a different period than this star here. And that throws up an immediate red flag. That's something else is in this system. There's something else there. Now, doing some math, the astronomers were able to calculate the object, the third object that would have to be in this system for this star to have the period that it does. And they discovered that there's a third object there that's as identified by this red streak right here. This third object, which has a mass of about 4 or 5 times the mass of the sun, our sun, 4 or 5 times the mass of the sun. So astronomers look at this and they say, okay, we have one star here, we have one star here, and we have one unknown object right here. But that unknown object is really massive. It's 5 times the mass of the sun, but we can see nothing. We see nothing there. We only see the two stars. There is a third object, but we can't see it. And so my question to you all, everyone here in the YouTube chat room, if there is a third object in this system that's really, really massive, but we also can't see, what is it? What would that be? What possible object could that be? Does anyone have any questions for Jesse? Come on, there's got to be someone in the chat room. I know there's a delay, but there's got to be someone someone's going to know. If there's a third object in that system, but we can't see it, but it's very massive, what is it? You have to think hard about this, okay? The sun? No, it's not the sun. All right. Discover the Universe knows is the answer. Yes. Oh, there's so many questions. There's got to be people. It's not a comet. Good question. It's not a comet. It has 4 times the mass, 5 times the mass of the sun. I think I see the answer. Someone got the answer. It's there. Tate Krupa. It's not a blue giant. Nope. Tate Krupa got it. Truffle Dog got it. Helen Tam got it. That's right. It's a black hole. What you're looking at here is a video. This isn't real, but this is a video representing the data the astronomers collected. And this is the discovery of a black hole about 1,000 light years away from us in the system HR 6819. So you have 2 stars and 1 black hole all orbiting each other. This black hole is 4 or 5 times the mass of the sun, and it's about 1,000 light years away from us. It's the closest black hole that we have ever discovered. 1,000 light years away. Remember, that means it takes 1,000 years for light to travel from that system to your eye. Okay, so there's a long delay between those two. Although 1,000 light years is far, our galaxy is 100,000 light years across. So in terms of a galactic size, it's about 1% the size. So Good job, everybody in the chat room. There's a question there I see. So brown dwarf. Oh, so Katie TV log said brown dwarf. Brown dwarf we would have been able to measure. Brown dwarfs shine in infrared, so they don't shine very bright like our sun does, but we can see them in infrared, and our telescopes would have been able to see them. This was a completely dark object, and also brown dwarfs can't be 5 times the mass of the sun, so it's too big. Really great, really great ideas there in the chat room. Okay, I'm gonna go back. Okay, so there's some questions. Okay, is there any way people can see light coming from invisible stars? Well, stars by definition are not invisible. Stars create light, and every single star out there is going to shine in most of the electromagnetic spectrum. So you'd be able to see a star with, like, our sun shines quite brightly, and as does all stars in the universe. There are dimmer stars than others, but they all shine. So the ones that are dimmer, you just need to use bigger telescopes to see them. Why are black holes so bright? That's a good question. Technically, black holes are not bright. Black holes are dark. They do not shine. In fact, black holes are so gravitationally strong that the light, or any light near them, would get pulled in and pulled and made part of the black hole. So black holes don't shine. However, the areas around them can be quite bright if a star gets too close to a black hole and gets torn apart. That would be a very bright thing. But the black hole itself is not shining. It's the star being torn apart that's shining. And that's usually how we find black holes. The number one way we've ever found a black hole is by watching it destroy something. A black hole is normally dark. It's just sitting out there in space doing nothing. And then if a star gets close to it and gets torn apart, it gets really, really bright around it. And we see that through our telescopes, and we can infer that there's a black hole there. This is fine. The way we found this black hole was by purely through gravitational effects of a star orbiting it. Okay, maybe I should get off this slide here. So back to summarize this story, that little star right there at the center, that blue star, which is actually 2 stars, is not actually just 2 stars. It's 2 stars plus a black hole. It's 1,000 light years away. It's visible to the 2 stars are visible to the naked eye, which means if you happen to be in the southern hemisphere and you can find the constellation of Telescopium, you can find that star and you can point at it with your eyes, and you can say, right there, orbiting with those 2 stars in that little section, bottom corner of Telescopium, is a black hole, the closest black hole to Earth that we've ever found. Ooh, okay, that was okay. Are black holes like a portal? No, black holes are not. Black holes are objects, they have mass, and you don't go into a black hole, you fall onto a black hole. It's a thing with gravity that you fall onto. Now, we don't really understand a lot of what's going on in there because we can't actually observe inside of a black hole, because inside of the event horizon, the point by which light cannot escape. But it does have mass, and things do orbit them. And it's not, a lot of people like to think of black holes as a hole in the universe. And mathematically, the amount of folding of the universe is really interesting. But there's no reason to believe that it would be like a portal or a wormhole to anything. The mathematics of general relativity seem to suggest that it's possible, but we have no evidence to suggest that it does happen. Did we find wormholes yet? Not that I'm aware of. Sorry, no wormholes, no portals. Is there white holes is a question. White holes are the opposite of a black hole. So a black hole is something that has such strong gravity that it pulls light in and pulls stuff really close. The opposite of that would be a white hole, which pushes things away really, really strongly. Again, within the mathematics of general relativity, what we use to describe gravity, if I'm not mistaken, a white hole is technically possible, but we have no evidence that a white hole exists in the universe. And another way of framing that is that there is also, so when I say that a white hole is technically possible, that doesn't mean that it is possible. So the framework of gravity in the universe, what we call general relativity, also doesn't have a preference for time direction, which means we perceive time as moving in a certain direction. We say forward, time moves forward, but there is no reason for time to be moving forward within our understanding of the universe. It's just that's the way we perceive it. That doesn't mean time goes backwards. It just means that we haven't really figured out how all that stuff works yet. So white holes are an interesting thing to think about. Backwards in time is an interesting thing to think about. And as are like wormholes or white holes, like all of those things are really interesting to think about and can somewhat be described through the mathematics, but there's no evidence to suggest that any of that stuff exists. Okay. So that's the story number one. And I'm like 20 minutes in. So that's story number one. We astronomers have found a black hole super close to us that is in a triple system, 2 stars, 1 black hole. Very cool. Let's move on to the next one. I want to talk about planets around stars. So this is an image of the night sky. This is in the north this time. This is the northern hemisphere, and you can see the Hercules. There's Hercules there, and there's Lyra with Vega. Vega is a very bright star, and right here, there is a star that we're going to talk about today. And the reason we're talking about it is because a new planet was discovered around it. It already had 2 planets, and a third planet was discovered around it called which has a really interesting mass. Now, the way they found this planet, this third planet, is exactly in the way that they found the black hole in the other star system. And that's because planets do tug just a little bit on stars. If you have a massive enough planet like Jupiter, or like this planet here, the star at the center of the system will wobble just a little bit. Wobble, wobble, wobble. And that wobble tells you that there's something there tugging on it, pulling on it with its gravity. And we can use the spectrum of the star, which is its rainbow. If you take the light from the star and you put it through a prism and spread it into a rainbow, we can use the rainbow of a star to calculate the mass of the object that is orbiting it. And that's how they found this third planet in this system. And it's a very special kind of planet, and I'm gonna talk about it with respect to our solar system. Okay. How big is Vega? There's a good question. How big is Vega? I don't know how big Vega is. I feel like we could Google that. Someone who's watching, Google how big is Vega, and we'll see how big it is. Do you mean mass or do you mean size? They're 2 different things, right? Because mass and size are very different. I think that's all the questions in the chat room. Yeah, okay. Oh, I think Lindsay got it. Vega is 1.6 million kilometers wide. Now the question is, how wide is the sun? Which I think the sun is about half that size, if I'm not mistaken. Okay, so here's our solar system. We have the sun at the center. We have 4 terrestrial planets. We have 4 gas planets, and we have Pluto out there. We also have Ceres, which isn't pictured, right in between Mars and Jupiter. And we have the asteroid belt between Mars and Jupiter, and we have the Kuiper belt out beyond Neptune. And when we look at our solar system, we see a few different types of things. We see those terrestrial planets. These are the 4, Mercury, Venus, Earth, and Mars, right at close to the sun, that are made primarily of rock. They're rocky things that you stand on, that you could stand on if you went there. And they all kind of share similar properties. They're similar sizes, similar materials. There's the asteroid belt, small chunks of stuff in between Mars and Jupiter. Then you have the 4 gas giant planets. Okay, these planets are primarily made of gas. There may be some kind of rocky core at the center of them, but in general, it's mostly gas that makes these planets up. So you're looking at the tops of clouds of Jupiter, Saturn, Uranus, and Neptune. Those are mostly made of clouds. Now, that doesn't mean that it's all fluffy and billowy. If you were to dive into Jupiter, you would very quickly get to a very, very dense, hot gas. So dense and hot that you wouldn't be able to survive. And and that's a very different thing. When we think of gas, when we think of atmospheres, we think of something very loose and tenuous, like our atmosphere. But you have to imagine it being super dense and hot. Now, we also have way out at the edge a bunch of icy things. We have these icy objects out here. Pluto is one of those, and they're kind of like a mix between ice and rock. And this is our general makeup of the solar system. We have terrestrial planets, we have gas planets, we have little rocky things, and we have little icy things. And that is the basic 4 categories of things that orbit the sun in our solar system. Now, the interesting thing is, let's take a look at Earth versus Neptune. Okay, so we have Earth here on the left, and this is Neptune on the right, Earth and Neptune. And Earth is about like 5 times smaller than Neptune, and like I think it's like 15 times less mass or something like that. So Earth is very, very different from Neptune. Earth is a rocky planet. Neptune is considered a gas giant planet. The really interesting thing about exoplanet research, which is the research of studying other planets that orbit other stars, is that we found a 3rd type of planet that sits in between these 2. Okay, these are called super Earths or dwarf gas giants, dwarf gas giant planets. Or dwarf Neptunes, maybe, I don't know. So there is a 3rd type between rocky terrestrial planet and gas planet. There's one in the middle that we are calling a super Earth, and we found lots of them out there. They seem to be both rocky and gassy at the same time. They have sort of similar densities and similar and a size that's in between the 2 of them. In fact, if you look at all the planets that have been discovered, I'm going to walk you through this thing here. So this is the sizes of planets that have been discovered, totals as of 2013. But the point I want to make is doesn't need to be up to date for that. So here in this graph, we have Earth-sized planets over here, so this is 1.25 times the radius of Earth. So a little bit bigger than Earth and smaller. You have about 600. You have the gas giant planets, which are over here, like Neptune to Jupiter. So we have lots and lots of those. Those are much bigger than Earth. But then there's this category, this super Earth category, that's between 1.25 and 2 times, or 1.25 and 3 times the mass of, or the size of Earth. And look at that, there's thousands of planets that we've discovered in that category that does not exist in our solar system. So we've found, go back to here. We have found out in the universe a whole new category of planet that we don't see in our solar system. Well, this planet that sits in between terrestrial and gas planet. And it's really weird. It'd be kind of cool if we had one, but we don't have one. And it shows you how important it is to go study other systems, because you can't learn everything there is to know about the universe just by looking in your own backyard. You have to go look all over to see what's going on. And our solar system, while it has lots of interesting different things, doesn't have everything the universe has to offer. And it also may make you wonder what other kinds of planets might be out there that we haven't discovered yet. And this system, if I go back to right here, the star, there's a star right there that already had 2 planets orbiting it. They found another super Earth that's orbiting that star right there in the sky. It's a really interesting field. Exoplanet research has only been around for about 25 years or so, maybe 30 years in the ramp up to it. And as we've learned more about planets, we've found some really interesting things. So those are the 2 stories that I wanted to talk to you about today. There is the black hole that was discovered in the triple system, and the super Earth that was discovered around that star right there in Hercules, and what a super Earth planet is. And let's jump onto some questions. Can there be rocky planets as big as Jupiter? No, there cannot be. There's just no way to pack that kind of mass together into one place. And can you clarify the difference between radius, diameter, and circumference? The kids are getting confused about measurements. Oh my gosh. Okay. Let's see if I can draw this. Okay. There's a circle, right? diameter is the width of the circle. How all the way across the circle. That's the diameter. Okay. Radius is half of that. So the radius is half of the diameter. And the circumference is all the way around the edge of the circle. So the diameter of Earth is, I think the diameter of Earth is 12,000. Yeah, I think that's about right. I think the diameter of Earth is 12,000 kilometers. And so the radius is half of that. And then to calculate the circumference, it's 2 times pi times the radius. And you get the circumference. If Mercury is near the sun, oh, let's go to my solar system. Okay, if Mercury is the closest planet to the sun, how come Venus is the hottest planet? And that is because Venus has a very, very thick atmosphere, and an atmosphere made mostly of carbon dioxide, which is a heat trapping gas. A good way to think about it would be, imagine you were at a campfire, say you went camping, or you were at the beach or whatever, and there's a campfire, and you were in like a tank top and shorts, and you were very close to the fire, and then you had a friend who was a little bit further away from the fire, but in a full snowsuit, complete snowsuit, and the snowsuit was holding all that heat into your friend. That person in the snowsuit is going to be warmer than a person closer to the fire because their snowsuit is trapping all the heat close to them, keeps them nice and warm, keeps them really toasty. Venus has a very thick atmosphere and mostly made of carbon dioxide. It traps all the heat from the sun and it stays hot. Whereas Mercury has 0 atmosphere. It has no atmosphere at all. It doesn't trap any heat. And so that it does get really hot on the daytime side, but on the nighttime side, the heat just goes right back out into the universe and it doesn't get trapped and stay there. And that makes Mercury a little less hot. Mercury's still hot. The daytime side is like 400 degrees Celsius or something like that. But the daytime side on Venus is just a little bit hotter than that. So any other questions from the chat room? Oh, they got people telling them in the chat room what what the circumference, diameter, and radius are of circles. Another cool thing to note is that most planets are not perfectly circular anyway, or perfectly spherical. Like Earth is what we call an oblate spheroid, which means it's actually a little bit squished. It's almost got kind of a pumpkin feel to it, where it's not as tall along the north-south as it is around the east-west. But I'm getting into other things. Hello.
I figured I'd come so you didn't have to just talk to yourself. I'm waiting to see if there's any other questions that come in, but we are also really close to the end of our time.
Yeah, I think this is the first time that I stayed within the time limit.
And you did 2 subjects.
Yeah, I did them very, very quickly. They're both, and they both kind of overlapped with each other. They're both about discovering things using the gravitational effect around another star.
Yeah.
What is the biggest black hole? There's a question. What is the biggest black hole that exists? Okay, so by biggest, I assume you mean most massive, because size of things and mass of things are 2 different things. The black hole at the center of our Milky Way is 4 million times the mass of the sun. But the black holes that I studied in my grad work were billions of times the mass of the sun, and I'm pretty sure that the most massive one was something like, I want to say something like 20 or 30 or 40 billion times the mass of the sun with a B. But I can't remember off the top of my head. But these are ones that these are supermassive black holes that sit at the centers of galaxies. The real actually interesting question is not what's the most massive one, but what's the most massive one compared to the galaxy that it lives in? Because usually the mass of the black hole scales with the galaxy. So if the galaxy is really big, the black hole mass is really big at the center. But there are some galaxies out there that are really small that still have really massive black holes at the center. And that's kind of confusing for everybody. And we don't really know why that happens. Hopefully that answers your question. I think that's it.
I think it does. One of the things I wanted to mention is there were a few questions about Astro news and how often it happens. And I just want to clarify that it just is like a short, cute way of saying news about astronomy. So when people discover things about astronomy, it goes in the news and we hear about it. So Astro News just is when new discoveries are made, and you can go and look on Google or your favorite newspaper to find out what other astronomy news is coming up. So Jesse was just talking to us today about some new things that astronomers have discovered recently.
Someone posted in the chat room search results about the largest supermassive black hole. According to their results, it was 6.5 billion times the mass of the sun, and that's in M87. But M87 is really super close to us. I mean, in terms of the way I think, there are definitely there are more massive black holes out there than that, for sure.
That's cool. I'm trying to see, I think we got all the questions that we could. Some of the questions that we got, I tried to answer in the chat because they weren't entirely related to the subject today, but we are definitely coming back tomorrow with another topic for you. I should have looked it up while I was moderating the chat because I don't remember what we're doing tomorrow, but
someone cool will be talking, that's for sure.
Of course, somebody awesome will be talking. Thank you so much, Jesse, for joining us today. Unfortunately, this is Jesse's last time doing Astro at Home since we are winding down for... No. We're winding down at the end of the month, so Jesse won't be back. If you guys are happy with the presentation that you got from Jesse, send us your favorite emoji in the chat and just show him some love. Give him some hand clapping or hearts or pizzas.
There's lots of pizzas and pie. Is that pie?
Yeah, pumpkin pie.
A cat getting swallowed up by a black hole. What?
Yeah, they like to tell each other funny astronomy stories.
Okay, interesting.
Anyway, thanks so much, Jesse, for being here with us today. And thanks to everybody who's watching us live at home. Just a reminder that we do have those educational resources in the chat, or not chat, in the text description box below. Additionally, we still have that survey up. So if you've been watching Astro at Home and you want to give us a little bit of feedback on how much you enjoyed it, what was your favorite, what was your least favorite, that kind of thing, you can follow the link and fill out that survey for us. That would be helpful. And we'll be back tomorrow with somebody super cool to talk about more awesome space topics. So I guess we'll see you guys then.
Bye, everyone.
Bye, everybody.